Hello, in this lecture I will answer two questions. The first question is find out the radius of this circle that blocks coordinate ABCD. And in the second question we find out the length of this line segment AP is equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have quadrilateral ABCD that is inscribed by this circle. You know that AC is the diameter of this circle. In addition, you know that AB equals to BC. Again, our task is to find out the radius of this circle that blocks quadrilateral ABCD. So first of all, we define the side lengths of quadrilateral ABCD with letters. We define the length of side BA as A. And because of the fact that AB equals to BC, BC must be also equal to A, units in its length. We define the length of side AD as B, and we define the length of side CD of quadrilateral ABCD as C. So here we can implement Rule 7 in our drawing. Repeat quickly on Rule 7. According to Rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB. This is the diameter of this circle, and therefore, according to this rule, Rule 7, peripheral angle ACB must be equal to 90 degrees in size because it's subtends on the diameter of the circle. So any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in size. So we can implement Rule 7 in our drawing. Because in our drawing we have peripheral angle ABC that subtends on chord AC, that is the diameter of the circle, and therefore according to Rule 7, peripheral angle ABC must be equal to 90 degrees in its side. Likewise, we have also peripheral angle ADC that also subtends on AC, the diameter of the circle, and therefore it must be equal to 90 degrees in its size. So, in the next step, we will implement the Pythagoras theorem on both right angles. Implement the Pythagoras theorem on this right angle ABC, and in this right triangle ADC. This right angle ABC, and another right angle ADC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ABC, here by PT's evaluation for Pythagoras theorem, according to the Pythagoras theorem, in this right triangle ABC, AC square, that is the square of the hypotenuse, is equal to AB square plus BC square. And again, in this right triangle ABC, according to the Pythagoras theorem, AC square, this is the square of the hypotenuse, equals to AB square plus BC square. AC is the missing side, so we leave it as it is, so it is AC square equals to AB square. AB is A, therefore AB square is A square plus BC square. BC is also A, so BC square is A square. So in total, if you found out that AC square equals to A square plus A square, this is 2A square. According to equation 1, AC square equals to 2A square. In the next step, we will implement the Pythagorean theorem on this right triangle times ADC. Again, we implement the Pythagorean theorem on this right triangle times ADC. According to the Pythagorean theorem, in this right triangle ADC, AC squared, this is the square of the hypotenuse, is equal to AD square plus CD square. And again, in this right triangle ADC, according to the Pythagorean theorem, AC squared, that is the square of the hypotenuse, equals to AD square plus CD square. So AC is the missing side, so we leave it as it is, so it is AC square equals to AD square. AD is B, therefore AD square is B square plus CD square. CD is C, therefore CD square is C square. So in total, according to equation 2, we actually found out that AC square equals to B square plus C square. But according to equation 1, we found out that AC square equals to 2A square. So we have two different equations for AC square. Therefore, this is the first equation and this is the second equation for AC square. So in the next step, we get equation 3 that says that AC square according to equation 1 must be equal to AC square according to equation 2. So equation 3 says that AC square according to equation 1 must be equal to AC square according to equation 2. AC square according to equation 1 equals to 2A square, and it must be equal to AC square according to equation 2. AC square according to equation 2 equals to B square plus C square. In total, according to equation 3, if you found out that 2A square equals to B square plus C square. So here we divide this equation 3 by 2, and finally we get that according to equation 3, A square equals to B square plus C square over 2. actually it is given us the question that the perimeter of this quadrilateral ABCD is equal to 18 units in its length, and also it is given us the question that the area of this quadrilateral ABCD is equal to 16 square units in its size. So what is the perimeter? The perimeter of a quadrilateral is the sum of its side lengths. That is to say, the perimeter of this quadrilateral ABCD is equal to AB plus BC plus AD plus BC. So the sum of the lengths of quadrilateral ABCD, the sum of its side lengths equals to the perimeter, that is 18. So AB is A, BC is A, AD is B, and CD is C. So the sum of the side lengths of this quadrilateral ABCD equals to A plus A, that is 2A, plus B plus C. So in total, 2A plus B plus C equals to the perimeter of this quadrilateral ABCD is equals to 18 units in its length according to what is given as a question. Okay, again, according to this equation 4, the perimeter of quadrilateral ABCD equals to 18 units. In addition, this gives us the question that the area of this quadrilateral ABCD is equal to 16 square units in its size. Quadrilateral ABCD consists of two shapes. Two shapes that are two right angles. Therefore, the sum, the area of ABCD, the area of quadrilateral ABCD must be equal to the sum of the areas of those two shapes that it consists of. So the area of quadrilateral ABCD in total it must be equal to the area of the first shape that is consists of, actually the area of this right triangle ABC, plus the area of the second shape that triangle ABCD, that's quadrilateral ABCD consists of, the area of this right triangle ADC. And again, actually, we have here equation 5 that says that the area of quadrilateral ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the area of the triangle ABC, plus the area of the second shape that quadrilateral ABCD consists of, that is actually the area of the triangle ADC. We know that the area of quadrilateral ABCD equals to 16, so we substitute the area of quadrilateral ABCD by 16. So 16 equals to the area of the right triangle ABC. The area of this right triangle ABCD equals to the base AB times the height BC over 2. The base AB is A, the height BC is also A, so it is A times A over 2. That is to say, it is A squared over 2. So in total, we found out that the area of the right triangle ABC equals to A squared over 2 square units in its size, plus the area of the second shape, that is the area of this right triangle ADC. The area of this right triangle ADC is equal to the base AD times the height DC over 2. AD is B, DC is C divided by 2. So it is B times C over 2. There on the second step, there on the right by ADC equals to B times C over 2. So now we have found out that according to equation 5, 16 equals to A square over 2 plus B times C over 2. Here we will multiply this equation 5 by 2, and finally we get that according to equation 5, 16 times 2 is 32, so 32 equals to A square over 2 times 2 is A square, plus BC over 2 is BC. So total, according to equation 5, here we found out that (32) equals to A square plus BC. But according to equation 3, we already found out that A square equals to B square plus C square over 2. So in the next step, we substitute A square in this equation 5 by B square plus C square over 2. And you get that according to equation 5, (32) equals to A square, and A square is B square plus C square over 2, plus BC. So according to equation 5, we actually found out that 32 equals to B square plus C square over 2 plus BC. So here we multiply BC by 2, and then we will divide it by 2 in order to have a common factor with this expression. And finally we get that according to equation 5, (32) equals to B square plus C square over 2. So here BC times 2 is 2 times BC divided by 2. So in total, if we found out that according to equation 5, 32 equals to B square plus C square plus 2 times B times C over 2. Here we will multiply this equation 5 by 2. And finally we get that according to equation 5, 32 times 2 is 64. So 64 equals to B square plus C square plus 2 times B times C. We have the algebraic identity that says that A square plus B square plus 2 times A times B equals to A plus B square. So according to this algebraic identity, we get that B square plus C square plus 2 times B times C is equal to B plus C square is equals to 64. So in total, according to equation 5, we actually found out that 64 equals to B plus C square. Here we take a look out of this equation. And finally we get that moving to equation 5. The square root of 64 is 8, so 8 equals to b plus c, or b plus c equals to 8. While according to equation 4, found out that 2a plus b plus c equals to 18. So we substitute b plus c in this equation 4 by 8 from this equation 5. Again, that according to equation 4, we have 2a and b plus c is 5. B plus c is 8 according to equation 5. So the b plus c by 8 equals to 18. So according to equation 4, we found out that 2a plus 8 equals to 18. Here we subtract 8 from this equation 4, and finally get that 2a equals to 18 minus 8 is 10. So 2a equals to 10. Here we divide this equation by 2, and finally get that according to equation 4, a equals to 10 over 2 is 5. So a equals to 5 units and it's 10. So AB equals to A and A equals to 5. Here also BC also equals to A and A equals to 5 units in its length. So in the next step, we implement the Pythagoras theorem on this triangle ABC. The two perpendiculars are given us. We found out that each of them equals to 5. The only missing side is the hypotenuse, that is the diameter of the circle. By implementing the Pythagoras theorem on this side ABC, we find out the length of the diameter of the circle and the radius of the circle, that is the figure that we are looking for. This is the element that we are looking for in this question, will be equal to the diameter over 2. So we implement the Pythagoras theorem on this right triangle ABC. Here by PT is the equation for Pythagoras theorem. So in the right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. And again, according to the Pythagoras theorem, in this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so we leave this it is, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25. Plus BC squared. BC is also 5, so BC squared is 5 squared, that is also 25. So En total, we should find out that AC square equals to 25 plus 25, that is 50. So AC square equals to 50. Here we substitute 50 by 25 times 2, so AC square equals to 25 over times 2. Here we take out all of this equation and find that AC, the value of the diameter of the circle, is equal to the square root of 25 is 5, and so inside the root we left only with 2. So actually found out that the length of the diameter of this circle, AC, is equal to 5 times square root of 2 units, and radius, the level that we are looking for this question, the radius R equals to the diameter AC over 2. That is to say it is 5 times square root of 2 over 2. So do that, I should know that the radius that we are looking for this question, that is the radius of this circle, equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, it is equal to 3.536 units in its length. So again, I should find out that the radius of this the radius of this circle equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, R equals to 3.536 units in its length. So we finish with the first question. In the next step, I present you the second question and solve the second question of this lecture. In the second question, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the drawing, this is the right triangle ABC. Inside this right line ABC we have a circle, so this circle is inscribed by the right triangle ABC. The length of this chord QP is equal to 24 units. This is line segment SQ, is equals to 25 units in its length. This is again ABC, this is right angle. Again, our task is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So first of all, we can implement rule 2 in our drawing. So repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common center point to a circle are equal. In the domain, we have a circle. This is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because if we focus on this common external point A, from this common external point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP equals to X, and therefore AQ must be also equal to X, according to rule 2. We define the point of tendency of tangent BC with this circle. This point is point M. We define the length of tangent BM as A. And we focus on this common external point B. From this common external point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to A, therefore BQ must be also equal to A, according to rule 2. So, here a point S. From point S, we have tangent SM, that is tangent to this point M, and we have a chord PQ, the extended chord QP, or PQ, touches point S. Again, the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10 in our drawing. I click quickly on rule 10. According to rule 10 is true in any circle, so according to rule 10, if AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So, in the moment, we have a circle. From this point, common external point P, we have tangent PT. This is tangent to this circle at point T. Likewise, we have here chord BA. The extended chord BA touches point P. So, in this moment, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So, as I mentioned before, if we focus on the common external point S, we have tangent SM, that is tangent to this circle at point M, and we have the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation is true, that SM square equals to SQ times SP. Again, SM square equals to SQ times SP. Hit again. If we focus on the common sum point S, can implement rule 10, according to rule 10, Sm squared equals to Sq times Sp. So Sm is the missing tangent, so we leave it as it is, so it is Sm squared equals to SQ is 25 times SP. SP in total is equals to SQ, that is 25, plus QP, that is 24. 25 plus 24 is 49. So in total, SP equals to 49 units in its length. So in total, we actually found out that Sm squared equals to 25 times 49. So here we take a root out of this equation. And finally we get that Sm, the length of Sm, is equal to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, Sm equals to 5 times 7, that is 35. Sm equals to 35 units in its length. Okay, this is a tangent Sm that is equals to 35 units in its length. What is the length for this missing master SB? For the law, it is very easy to see that SB in total equals to Sm minus Bm. Again, Sm minus Bm equals to SB. So as you know, if you remember that the missing 97 SB is equal to Sm minus Bm. So total SB equals to Sm is 35, plus Bm is 8 according to our definition. So in total, we should find out that SB equals to 35 minus a units in its length. So in the next step, we'll implement the bottom storm on this green right triangle. Okay. We have here CS is a or CM. CM is a tangent. So CM is a CM is a tangent. It is absolutely a straight line. So if we focus on the upper side of the straight line SM at point B, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas on one side of a straight line is equal to 180 degrees. So which areas we have at the upper side of SM at point B? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So now we have here the green right triangle SQB. So we implement the Pythagoras theorem of this green right triangle SQB. And according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle SQB, SQ square, that is the square of the hypotenuse, equals to QB square plus BS square. So write it down, SQ square equals to QB square plus SB square. And again, in this right triangle SQB, according to the Pythagoras theorem, SQ square equals to QB square plus SB square. SQ is 25, therefore SQ square is 25 squared, that is 625, and it is equals to QB square. QB is 8, therefore QB square is a square plus SB square. SB is 35 minus 8, therefore SB square is 35 minus 8 square. So in total, we should find out that 625 equals to a square plus 35 minus a square. So we'll open the brackets on this side of the equation, this expression, and we get that 625 equals to a square plus 35 minus a square. 35 minus a square equals to 35 square, that is 1225 plus a square minus 2 times 35 times 8 is minus 78. So total we should find out that 625 equals to a square plus 1225 plus a square minus 78. So here we subtract 625 from this equation. And we get that 0 equals to a square plus a square is 2a square. Minus 78, 1225 minus 625 is 600. So in total, we should find out that 0 equals to 2a square equals 0 equals to 2a square minus 78 plus 600. Here we divide this equation by 2 and find again that a square minus 78 over 2 is minus 45a. 600 over 2 is 300 equals to 0. So a square minus 45a plus 300 equals to 0. So this is a quadratic equation. But again, this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. This is the general formula. A, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, to the following general formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say a squared minus 45a plus 300 equals to 0. The coefficient a equals to 1. The coefficient b equals to minus 45. and the coefficient c equals to 300. And the variable that we're looking for in this equation is a, so x equals to a. So we have all the data in order to find out the value of a. You just have to put the data inside this general formula for x, and in this way we find out the value of the values of a, because x equals to a. A is the variable that we are looking for. So we do it now, and we get that again x equals to a, so a equals to minus b. B, the coefficient b equals to minus 45, therefore minus b is minus 45, that is plus 35, plus minus square root of b squared. B is minus 45, therefore b squared is minus 45 squared, that is 1225. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. C is 300, so minus 4 times 300 is minus 1200. So in total, minus 4 times AC equals to minus 1200 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we found out that a equals to 35 plus minus square root of 1225 minus 1200 over 2. So a equals to 35 plus minus. Inside root we have 1225 minus 1200 is 25. So inside root we'll have to leave 25 over 2. In total, we found out that a equals to 35 plus minus, so the square root of 25 is 5 over 2. So here we have two solutions to the possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20 units in its length. Well, according to the second solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 30, and 30 over 2 is 15. So the second solution for a is that a equals to 15 units in its length. Okay, so in the next step we will do a construction. That is to say, from point A we will go perpendicular on QP. This is an associated triangle. Triangle AQP is an associated triangle. Why triangle AQP is again triangle is an associated triangle because side AQ equals to side AP. The base of the associated triangle is QP. So from point A we go perpendicular on the base QP. The associated green triangle, triangle AQP. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in the base QP. This point is point Z. So we have associated green triangle AQP, and we have the perpendicular to the base, this AZ. So here I can implement rule 21. Okay, quickly on rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. So in the drawing, we have the associated triangle, triangle ABC. Triangle ABC, AB equals to AC, therefore it is an associated triangle. From point A, we draw perpendicular AO to the base BC. AO is the perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule, rule 21, the perpendicular AO bisects the base BC. Again, the perpendicular AO is not only perpendicular to the base, but it is also bisect the base BC. That is to say, it divides the base BC into two halves. BO is the first half, OC is the second half, and each half, of course, equals to BC over 2, because BC has been bisected into two halves. So the first half BO equals to BC over 2, and the second half also equals to BC over 2. So BO equals to OC equals to BC over 2. So we can actually implement rule 21 in our drawing. What I put in our drawing, we have an associated triangle APQ. QP is the base. From point A, we go perpendicular AZ to the base QP. According to rule 21, that the perpendicular AZ bisects the base BC into two halves. The first half is QZ, is equals to QP over 2. The second half is ZP, that also equals to QP over 2. So if you know, according to rule 21, the perpendicular AZ bisects the base QP into two halves. The first half QZ is of course equals to the second half ZP, and each half equals to QP over 2, of course. This again, triangle, again associated triangle, triangle AQP. The perpendicular AZ bisects the base QP into two halves. The first half is QZ, and it of course equals to the second half ZP, and each half equals to QP over 2. QP is 24, therefore QP over 2 is 24 over 2. QP over 2 equals to 24 over 2. That is 12. From this equation, we learn that QP equals to ZP equals to 12. QZ equals to ZP equals to 12. So the first half of the base QP is QZ, it is 12. The second half ZP is of course also equals to 12 units in its length, according to rule 21. Actually, those two angles, this is angle AQP and this is angle SQB. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define angle AQP as alpha, then angle SQB must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in this right triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Or equal 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in this right triangle SQB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. Actually, it is very easy to say from the drawing itself that those two right triangles they are similar to each other according to angle similarity. So, well, this is to say the right triangle AQZ, the right triangle AQZ is similar to this right triangle SQB. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So in total, we found out that all the triangles of this right triangle SQB are correspondingly equal to all the triangles of this right triangle AQZ, and therefore those two right triangles are similar to each other according to angle similarity rule. So it is done, we found out that the right triangle SQB, this is the right triangle SQB, is similar. This is the sign of similar to this right triangle AQZ. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of this right triangle SQB over side AQ of this right triangle AQZ is equal to side QB of this right triangle SQB over side QZ of this right triangle AQZ. So it is on. So we should found out that SQ over AQ equals to QB over QZ. Again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of the right triangle SQB over side AQ of the right triangle AQZ is equal to side QB of the right triangle SQB over side QZ of the right triangle AQZ. SQ is 25. Over AQ is X. X is the variable that we are looking for in this question. So AQ is X. And it is equals to QB. QB is A according to our definition. Or QZ. QZ equals to 12 according to rule 21. So QZ equals to 12. So in total, we actually found out that (25 over x equals to a over 12). Here we cross multiply this equation, and finally we get that 25 times 12 equals to a times x. So a times x equals to 25 times 12, that is 300. A times x equals to 300. So here we divide this equation by a, finding that x equals to 300 over a. We actually found out that we have two solutions that are possible for a. Cube equals to bm equals to a. So in order to find out which solution is the correct solution for a either equals to 15 or 20. In order to find out which is the right solution for the value of a, we analyze this right angle ABC. So I copied this right angle ABC in a new page and we analyze this right triangle ABC. This is right angle ABC, that is the point from the original drawing. So we have here, when we find the center of this circle, this point is point O. Point M is the point of tendency of tangent BC with this circle. We define the radius of this circle as R. In the next step, we join points O and M together by straight line. Point O is the center of this circle, point M is the point of the circle itself, therefore OM is the radius of this circle, that equals to R according to our definition. The radius OM, that equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, point Q is the point of tendency of tangent AB with this circle. So we join points O and Q together by a straight line. OQ is of course the radius of this circle, that is equals to R. I'll not repeat on the same explanation. According to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. So in quadrangle OMBQ we have 1, 2, 3 degrees, and therefore this fourth missing angle also equal to 90 degrees in its size. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle QOBM we have 4 angles, and therefore we can relate to quadrangle QOBM as a rectangle, although it is actually a square. So I write it down. Polygon OQBM is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle QOMB, side QB equals to the opposite side OM. But OM is R, therefore the opposite side QB must be also equal to R units in its length. So actually QB equals to A and A equals to R. So QB equals to therefore the radius of this circle that is R. In the next step, we'll do a construction, that is to say, we'll extend the radius MO by a straight line until it touches the circle. And we find the touching point of the extended radius MO with this circle. This point is point Z. When you extend a straight line by a straight line, the result MZ must be also a straight line, so MZ is definitely a straight line. So first of all, MZ is a straight line, so we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line ZM at point O? We have this angle that is right angle plus this missing angle, total must be equal to 180 degrees according to our field. Therefore this missing angle must be equal to 90 degrees in its size. Point O is the center of this circle, point Z is the point of the circle itself, therefore OZ is the radius of this circle, that equals to R. What is the definition of the straight line MZ? MZ is a chord. MZ touches the circle 2 points, M and Z, and therefore it is a chord. It is a chord that passes from the center of the circle, and therefore MZ is the diameter of the circle. So in the next step, we draw a tangent to the circle at point M. From AB, we draw a tangent to this circle at point Z. We define the touching point of the tangent with side AB, and this point is point T. So actually, TZ is a tangent to this circle at point Z. The radius OZ is equals to R. The radius OZ is drawn to point Z, that is the point of tendency of tangent TZ with this circle. And whenever your radius is drawn to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to rule 1. So in polygon TZ or Q, we have 1, 2, 3 rectangles, 1, 2, 3 rectangles, and therefore this fourth missing angle equal to 90 degrees in size. So I can write polygon TZ QO as a rectangle, although it is actually a square. It is a rectangle. Because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle TZOQ, side ZO equals to the opposite side TQ, but ZO is out, therefore the opposite side TQ must be also equal to R units in its length. We actually found out that QB equals to R and R equals to A. QB equals to R and R equals to A. Write it down. Let's say that QB equals to R and R equals to A. Okay. What is the left for AQ is, of course, the variable that we're looking for in this question. This is x. And AQ equals to x. What is the value of x? X equals to AQ, and AQ equals to AT plus TQ. And AQ equals to AT plus TQ. So AQ equals to AT plus TQ, that is R. So AQ in total equals to AT plus R. So AQ equals to AT plus R, and AQ of course equals to X. So A equals to R while X equals to AT plus R. X equals to AT plus R, and because of the fact that AT is a positive number, AT plus R is definitely greater than R. Again, AT plus R is definitely greater than R. So you can write here that AQ is greater than R. Again, AT plus R is greater than R. And from this inequality, we derive that X is greater than A. Again, X is greater than A. So found out that we have two solutions that are possible for the value of A, either equals to 15 or A also can be equal to 20. We have two solutions for A. A could be equal to 20 or A also could be equal to 15. And again, there are two solutions that are possible for A. A could be equal to 20 or A also could be equal to 15. We just right now found that X is greater than A. X is greater than A. And we have already found out that X equals to 300 over A. Now here that X equals to 300 over A. So if A equals to 15, then X equals to 300 over 15. This is actually 20. But if A equals to 20, then X equals to 300 over 20, that is 15. X equals to 15. So X that is equals to 15 is definitely less than 8 is equals to 20. Yeah, X is equals to 15 is definitely less than 8 is equals to 15. So this holding inequality we get that x is less than a. It contradicts the fact that x must be greater than a. So a contradiction. So we cancel the solution. This solution is the correct solution. And we are only the second solution. If x equals to 20, then a equals to 15. 20 is definitely greater than 15. So can I do that 20 is greater than 15? And from this inequality we get that x is greater than a. Yeah, x is greater than a. So this is exactly what we already found out, that x must be greater than a. And therefore, the final solution to the question is that the length of AP is equals to x is equal to 20 units in its length. That is the answer to the second question. I'll repeat again. The length of this line side AP is equal to x is equal to 20 units in its length. So finish with the second question. In the next step, I will summarize the lecture. I will start with the first question, of course. We will repeat on the first question. On the second solution. Our task in the first question is to find out the radius of this big circle that blocks this quadrangle ABCD. So in the drawing, we have quadrangle ABCD that is inscribed by this big circle. In addition, you know that AC is the diameter of the circle. We also know that side BA is equal to side BC in this quadrangle ABCD. Again, our task is to find out the radius of this circle. We also know that the perimeter of this quarter circle ABCD is equal to 18 units in its length. That is to say, the sum of its side lengths, the sum of the side lengths of this quadrangle ABCD is equal to 18 units in its length. That is to say, AB plus BC plus CD plus DA in total is equal to 18 units. And finally, we also know that the area of this quadrangle ABCD is equal to 16 square units in its size. Again, our task is to find out the radius of this circle that blocks quadrangle ABCD. So first of all, we define the length of quadrangle ABCD with letters. We define the length of AB is A. The length of BC must be also equal to A because they are equal to each other on their lengths. AB equals to BC according to what is given as the question. Likewise, the length of AD is defined as B, and the length of side CD equals to units in its length. So In the first step, we implemented Rule 7 in our drawing. So, repeat quickly on Rule 7. According to Rule 7, if a peripheral angle is subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB that subtend on the diameter of the circle, that is called AB. And therefore, peripheral angle ACB equals to 90 degrees in its size. So according to this Rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. So we can implement Rule 7 in our drawing. Once in our drawing, we have peripheral angle ABC that subtend on the diameter of the circle, called AC. Therefore, it must be equal to 90 degrees inside according to Rule 7. Likewise, peripheral angle CDA also subtend on chord AC, that is the diameter of the circle. Therefore, according to Rule 7, it must be equal to 90 degrees in its size. In the next step, implemented the Pythagoras theorem on both those two right angles. So in the first step, we implemented the Pythagoras theorem on this right angle ABC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in the right angle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Okay, again, in this right angle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so electricity. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So in total, AC squared equals to AB squared plus BC squared, that is to say AC squared equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared. This is according to equation 1. In the next step, implemented the Pythagoras theorem on this right angle ADC. If I find ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to CD squared plus AD squared. And again, in the right angle ADC, according to the Pythagoras theorem, AC squared equals to AD squared plus CD squared. AC is the missing side, so electricity is equals to AD squared. AD is B, therefore AD squared is B squared plus CD squared. CD is C, therefore CD squared is C squared. So in total, AC squared equals to B squared plus C squared. So I have two different equations for the value of AC squared. AC squared equals to 2A squared, or AC squared equals to B squared plus B squared. B squared plus C squared. So, therefore, we created equation 3 that says that AC squared according to equation 1 must be equal to AC squared according to equation 2. Again, according to equation 3, AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2, that equals to B squared plus C squared. So in total, we should hold on that according to equation 3, 2A squared equals to B squared plus C squared. Here we divided this equation by equation 3 by 2, and finally found out that A squared equals to B squared plus C squared over 2. This gives us the equation that the perimeter of this quadrangle ABCD is equal to 18 units. That is to say, AB that is A plus BC that is also A, plus CD that is C, plus DA that is B, in total is equals to 18. A plus A is 2A, so 2A plus B plus C equals to 18. 2A plus B plus C equals to 18. Likewise, we also give us the equation that the area of this quadrangle ABCD is equal to 16 square inches in size. But this quadrangle ABCD consists of those two right angles, and therefore the area of quadrangle ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, the area of this quadrangle ABCD in total must be equal to the area of this right angle ABC plus the area of the other shape, that's the area of this right angle ADC. And again, the area of the big quadrangle ABCD must be equal to the area of the first shape that it consists of. This is actually the area of the right triangle ABC plus the area of the second shape, that is the area of the right triangle ADC. The area of the ABCD, the area of quadrangle ABCD is 16, so we solve the area of the ABCD, the area of quadrangle ABCD by 16. is equals to the area of the right triangle ABC. The area of the right triangle ABC equals to the base AB, that is A times the height BC, that is also A over 2. So it is A times A over 2, that is associated A square over 2. So the area of the right triangle ABC equals to A square over 2 plus the area of this second shape, that is quadrangle ABC consists of the area of this right triangle ADC is equals to the base AD, that is B times the height CD, that is C over 2. So it is BC, B times C over 2. The area of the second shape equals to BC, B times C over 2. So total according to equation 5, 16 equals to A square over 2 plus B C over 2. Here we multiply this equation by 2 and find that 16 times 2 is 32, so 32 equals to A square plus B C. And again, if we found out that according to equation 5, (32) equals to A square plus BC. But according to equation 3, we only found out that A square equals to B square plus C square over 2. A square equals to B square plus C square over 2. So actually, you can substitute A square in this equation 5 by B square plus C square over 2. We did it, and actually found out that 32 equals to A square is B square plus C square over 2 plus BC. So here we multiply BC by 2 and then we divide it by 2 in order to a common factor of this expression. And we found out that 32 equals to B square plus C square over 2, and we have 2 times BC over 2. So in total we found out that 32 equals to B square plus C square plus 2 times B times C over 2. Here we multiply this equation 5 by 2, and we found out that 32 times 2 is 64 equals to B square plus C square plus 2 times B times C. We have the algebraic identity that states that A square plus B square plus 2 times A times B equals to A plus B square. And therefore, according to this algebraic identity, B square plus C square plus 2 times B times C, B square plus C square plus 2 times B times C will be equal to B plus C square. So we get that 64 equals to B plus C square. Here we took out of this equation, and we found out that the square root of 64 is 8, so 8 equals to B plus C. This is equation 5. B plus C equals to 8. But according to equation 2, we only found out that 2A plus B plus C equals to 18. So we can substitute B plus C in this equation 4 by 8 from this equation 8, because B plus C equals to 8. We did it, and we found out that according to equation 4, 2A plus B plus C and B plus C is 8 equals to 18. So in total, according to equation 4, we found out that 2A plus 8 equals to 18. Here we subtracted 8 from this equation, and finally found out that 2A equals to 18 minus 8 is 10. So in total, 2A equals to 8. Here we divided the equation by 2, and finally found out that A equals to 10 over 2, that is 5. So B equals to A and A equals to 5. BC also equals to A and A equals to 5. So in the next step, we implemented the Pythagoras theorem on this right triangle ABC. This right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Okay, again, according to the Pythagoras theorem, this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So I already mentioned before, we have AB is 5, AB is 5, therefore AB squared is 5 squared, that is 25. Likewise, BC is also 5, therefore BC squared is 5 squared, that is 25. So in total, AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. Here we substitute 50 by 25 times 2. So AC squared equals to 25 times 2. Here we took out of this equation and found out that AC, the missing diameter AC, there's also the hypotenuse of the triangle, the missing diameter AC is equals to the square root of 25 is 5 times square root of 2. AC equals to 5 times square root of 2. The diameter AC equals to 5 times square root of 2, and the radius of this circle, that is the radius that we are looking for, must be equal to the diameter over 2. That is to say, radius R equals to the diameter AC over 2. AC is 5 times square root of 2, and therefore the radius must be equal to 5 times square root of 2 over 2, that is 3.536 units in its length. So in total, we should find out that the radius of this circle is equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, the radius of this circle R equals to 3.536 units in its length. So finish to repeat on the first question. In the next step, repeat on the second solution of the second question. Our task in the second question is to find out the ref of this line segment AP that equals to x. We have to find out the value of x. So in the moment we have the right angle ABC, angle ABC equals to angle in its side. And we have also, this is line segment QS that is equals to 25 units in its length. This is called QP that is equals to 24 units in its length. And again, our task is to find out the ref of line segment AP that is equal to x. We have to find out the value of x. So in the next step, we implemented rule 2 in our drawing. This is rule 2, according to rule 2. The lengths of two tangents from a common standpoint to a circle are equal. So in the drawing, we have a circle. This is the common standpoint point P. For this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And the moment for this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. Why put in our drawing? If we focus on this common standpoint point A, for this common standpoint point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP is x, therefore AQ must be also equal to x units in its length, according to rule 2. Likewise, we define the point of tendency of tangent SC with this circle. This point is point M. We define the ref of tangent BM SA. For this common standpoint point B, we have two tangents to this circle, tangent BM and tangent BQ. Therefore, the two are equal to each other. That is to say, BM equals to BQ, but BM is there, therefore BQ must be also equal to A units in its length. So, in the next step, we implement rule 10 and to this common standpoint point S. For this common standpoint point S, we have tangent SM, that is tangent to this circle point M. Likewise, we have a called QP that is extended until it touches point S. So all the requirements for rule 10 are satisfied, and therefore we can implement rule 10. I think we have rule 10. Only for rule 10. Rule 10 is true in any circle. So in any circle, if AB is any chord in the circle and PT is a tangent to the circle, then the following equation is true, that PT square equals to PA times PB. And PT square equals to PA times PB. So in the drawing, we have a circle. This is tangent PT, this is tangent to the circle, that's point T. Likewise, we have chord BA. The extended chord BA touches point P. So So in this line, the following equation is true, that pt squared equals to pa times b, pt squared equals to pa times pb, again pt squared equals to pa times pb. So the mentioned before, we can definitely implement all in our drawing. So SM is tangent to the second point M, the extended chord PQ, largest point S, the whole point to 10, SM squared equals to SQ times SP, and SM squared equals to SQ times SP. Only to 10, SM squared equals to SQ times SP. SM is the missing side, the tangent SM is the missing side, so it is equals to SQ that is 25 times SP, SP total equals to SQ that is 25 plus QP that is 24. So SP total equals to 25 plus 24 that is 49. So here we have SM equals to SQ that is 25 times SP that is 49. Here we took out all of this equation and find out that SM equals to the square root of 25 is 5 times the square root of 49 that is 7. So total SM equals to 5 times 7 that is 35. Tangent SM equals to 35 units in its length. What is the length of this missing 97 SB? From the drawing it is very easy to see that SB in total equals to SM minus BM. And SB equals to SM minus BM. So SB total equals to SM that is 35 minus BM that is 8. So total SB equals to 35 minus units in its length. The next step, we implemented the Pythagoras theorem on this right green triangle, triangle SQB. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in the right green triangle SQB, it means that SQ squared, that is the square of the hypotenuse, must be equal to QB squared plus BS squared. Okay, the end right triangle SQB, according to the Pythagoras theorem, SQ squared, that is the square of the hypotenuse, must be equal to QB squared plus SB squared. The hypotenuse QS equals to 25 units inside, therefore QS squared is 25 squared, that is 625, and it's equals to SB to QB squared. QB is 8, therefore QB squared is 8 squared, plus SB squared. SB is 35 minus 8, therefore SB squared is 35 minus 8 squared. So total, if you know that 625 equals to 8 squared plus 25 minus 8 squared. So we open the brackets of this expression and finally found out that 625 equals to 8 squared plus 35 minus 8 squared equals to 35 squared, that is 1225 plus 8 squared minus 2 times 35 times 8, that is 178. Here we subtracted 625 from this equation, so in this side of the equation we have nothing, that is to say 0. While on the other side of the equation we have a squared plus a squared, that is 2a squared, 178, and we have 1225 from 625 is 600. So in total, we should find out that 0 equals to 2a squared, 178 plus 600. Here we divided this equation by 2 and finally found out that 0 over 2 is 0, 2a squared over 2 is a squared, 178 over 2 is 145a, and 600 over 2 is 300. So in total, we should find out that a squared 145a plus 300 equals to 0. Again, I should find out that a squared minus 35a plus 300 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. This is the general formula. A, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Over 2a. Now specific quadratic equation. First of all, this quadratic equation a squared minus 45a plus 300 equals to 0. The variable that we are looking for is a, so x equals to a. the variable the coefficient A equals to 1, the coefficient B equals to minus 45, and the coefficient C equals to 300. The only thing that is left to do is to put this data, or form a specific quantity in this formula for x, and in this way we get the value or the values of A, because x equals to A. So we did it, and again x equals to A, so A equals to minus B. B is minus 35, therefore minus B is minus 35. It's plus 35, plus minus square root of B squared. B is minus 45, therefore B squared is minus 45 squared, that is 1225, minus 4 times A times C. A is 1, so minus 4 times A is minus 4 times 1, that is minus 4 times C. C is 300, so minus 4 times 300 is minus 1200. So total minus 4 times A times C is equals to minus 1200 over 2A. A is 1, so 2A is 2 times 1, that is 2. So total of that A equals to 35 plus minus square root of 1225 minus 1200 over 2. 1225 minus 1200 is 25, so inside the root we left only with 25. So we have found out that A equals to 35 plus minus square root of 25 over 2. The square root of 25 is 5. So in total we have found out that A equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for A. The first solution for A is that A equals to 35 plus 5 over 2. 35 plus 5 is 40, so 40 over 2 is 20. So the first solution for A is that A equals to 20. While the second solution for A, the first solution is A equals to 20. The second solution for A is that A equals to 35 minus 5 over 2. 35 minus 5 is 30. 30 over 2 is 15. So the second solution for A is 15. So we have two solutions that are possible for A. In the next step, we did the construction. And then after the construction, we implemented all 21 in our domain. So from point A, we do perpendicular on QP. Again, from point A, we do perpendicular on QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and QP. This point is point Z. First of all, it is very easy to see that triangle AQP is an associated triangle because AQ equals to QP, and of course QP is the base of the associated triangle AQP. So for point A, we do perpendicular to the base QP. Again, from point A, we do perpendicular AZ to the base QP of the associated triangle AQP. So here we can implement rule 21 in our drawing. Okay, so we implement rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. So in the drawing, we have associated triangle ABC. AB equals to AC, therefore triangle ABC is an associated triangle. From point A, we do perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So according to rule 21, AO is not only perpendicular to the base, but it is also bisect the base BC. So perpendicular AO bisect the base BC. So the first half BO is BC over 2, the second half OC is also equals to BC over 2. So BO equals to OC equals to BC over 2. We can actually implement rule 21 in our drawing. Why? Because in our drawing we have the associated triangle AQP. From point A, we do perpendicular AZ to the base QP. According to 1, perpendicular AZ bisect the base QP. So the first half QZ is the first half QZ is equal to QP over 2. The second half ZP is also equals to QP over 2. First of all, this first half of QP equals to QZ, and also equals to the second half, of course, ZP. Each half equals to QP over 2. But QP is bisected. So it's alpha must be equal to QP over 2. QP is 24, so 24 over 2 is 12. So in total, from this equation, you have that QZ equals to ZP equals to 12. QZ equals to 12 and ZP also equals to 12 units in itself. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So in this angle, if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to all that I mentioned. So in this right green triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this green triangle QBS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this this angle must be equal to 90 degrees minus alpha according to the sum of the says that the sum of the angles in any triangle is equal to 180 degrees. It's very easy to see that those two right angles are similar to each other according to again similar to. That is to say, the right green triangle AQZ is similar to this right green triangle SQB. So why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So I shall find out that all the angles of this right triangle SQB are correspondingly equal to all the angles of this right triangle AQZ, and therefore those two right angles are similar to each other according to angle similarity rule. I shall find out that the right triangle SQB is similar. This is the sum similar. The right triangle AQZ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive this side SQ of the right triangle SQB or side AQ of the right triangle AQZ is equal to side QB of the right triangle SQB or side QZ of the right triangle AQZ. Again, side AQ of the right triangle AQZ and side SQ of the right triangle SQB or side AQ of this right triangle AQZ is equal to side QB of this right triangle SQB or side QZ of this right triangle AQZ. SQ is 25 over AQ is X, and this equals to QB, that is A, over QZ, that is 12. So we should find out that 25 over X equals to A over 12. Here we cross multiply this equation and finally found out that A times X equals to 12. A times X equals to 25 times 12. 25 times 12 is 300, so in total we have found out that A times X equals to 300. Here we divided the equation by A and finally found out that X equals to 300 over A. So actually found out that we have two solutions that are possible for the value of QB that is equals to A, or BM is also equals to A. A could be either equal to 20 or to 15. In order to verify what is the correct solution, we analyze this triangle ABC. So I copied this triangle ABC in the Olympiad and we analyze it in order to find out which is the correct solution for A, 15 or 20. So actually, this is the triangle ABC with the circle that inscribed on it with the point from the original drawing. This triangle ABC, we define the center of the circle as O. Point M is the point of tendency of triangle ABC with this circle. So we join points O and M together by set time. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that we define as R. the radius of M that is equals to 1, the radius of M is drawn to point M, that is the point of tendency, or that is BC with this second. Whenever your radius is drawn to the point of tendency, then BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, point Q is the point of tendency of tangent AB with this circle. So we join points O and Q together by straight line. OQ is of course the radius of the circle, this is equals to 1, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in quadrangle QOMB we have 1, 2, 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in size according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle QOMB we have 4 right angles, and therefore we can write to quadrangle QOMB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle QOMB, side OM must be equal to the opposite side QB. But OM is out, therefore the opposite side QB, this opposite side QB must be also equal to R unit in itself. So in total, QB equals to A and it also equals to R. In the next step, we did the construction, that is to say, we extended the radius of MO by side line until it touches the circle, and we find the touching point of the extended radius MO with the circle. This point is point Z. When you extend the radius MO is definitely a straight line. When you extend a straight line by straight line, the result MZ must be also a straight line. So MZ is a straight line. If you focus on the right side of the straight line MZ at point O, if the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have on the right side of MZ at point O? We have this angle that is the right angle, plus this missing angle, total must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in size. So we have here, in the next step, we did the construction, that is to say, from AB we go tangent to the circle at point Z. Again, from AB we go a tangent to the circle at point Z. So here TZ is a tangent to the circle at point Z according to our construction. So the radius OZ is equals to R, the radius OZ is 1 to point Z, that is the point of tendency of tangent TZ with this circle. And whenever your radius is drawn to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to rule 1. So in total, in this quadrangle TZOQ, we have 1, 2, 3 right angles. This angle equals to 90 degrees according to rule 3. So 1, 2, 3 right angles. And therefore this fourth missing angle must be equal to 90 degrees in size according to the rule I mentioned. So in total, in quadrangle TZOQ we have 4 right angles, and therefore we can write to quadrangle TZOQ as a rectangle because it has 4 right angles. So in rectangle TZOQ, the opposite sides are equal to each other. That is to say, side ZO must be equal to the opposite side TQ. But ZO is out, therefore the opposite side TQ must be also equal to R units in its length. Okay, so what is the ref? QB equals to A equals to R. And QB equals to A, according to our definition, we only found out that QB also equals to R. So you can write here that QB equals to R, and also it is equals to A. For one side, but we only found out that AQ in total is equals to X, this is the variable that we're looking for. AQ is equals to X, it is equals to AT plus TQ. So AQ in total equals to AT plus TQ. TQ is also in total AQ equals to AT plus R. So AQ equals to AT plus R. AT plus R, and AQ also equals to X. So you can write that AQ equals to AT plus R, that equals to X. And you have here QB is equals to R. QB equals to R, but R is definitely less than AT plus R. Again, R is definitely smaller than AT plus R because AT is a positive number. Okay? And for this law of inequality, we realize that A is smaller than X, or X is greater than A. So x is greater than a. We just like the found that x is greater than a, and we have two solutions that are possible for a equals to either 20 or 15. Now we'll find out which is the correct solution, 20 or 15 for a. We already found out that x equals to 300 over a. And we already found out that x equals to 300 over a. X equals to 300 over a. Therefore, if a equals to 20, it means that x equals to 300 over 20 is 15. Likewise, if a equals to 15, then x equals to 300 over 15, that is 20. So here x equals to 15 and a equals to 20, while here x equals to 20 if a equals to 15. So here we have x equals to 15. 15 is definitely less than 20, that is a. From this inequality we derive that x is smaller than a. This contradicts the fact that we found out that x is greater than a. Due to the contradiction, we cancel the solution and we left only with the other solution that is possible for a. A equals to 15. A equals to 15. X equals to 20. 20 is definitely greater than 15. And from this inequality, we derive that x is greater than a. X is greater than a according to our findings that x is indeed greater than a. So this is the correct solution for a. So if you found out that the length of line segment AP is equal to x is equal to 20 units. Again, the length of this line segment AP is equal to x is equal to 20 units. Okay, thank you very much.